Hi, my name is JHarmon and I'm taking all three classes. For KI2, the focus is on an audio amplifier system which takes an input signal and amplifies it for use by a speaker. To begin, the audio amplifier can be approximated as a linear time invariant system. Since the input to this system is sinusoidal, or equivalently a linear combination of complex exponentials, the output to the system in time domain can be seen as the transfer function of the system times the original input of the system. And so it's going to be scaled by the magnitude of the transfer function and shifted in phase by the phase of the transfer function. For the simple signal shown on the screen, we see that the input decomposes into two complex exponential terms, and since the system is linear and time invariant, we can see that the output of the system is the combination of the two individual responses. However, in reality, the system is not perfectly linear. At any point in the amplitude of the signal, we'll see that their nonlinearities exist. However, at smaller values for this amplitude, they are not substantial enough that they need to be considered. However, an increase, for example, in an amplitude of 10 millivolts to 200 millivolts, we see that new spikes occur in the frequent response at different harmonics. And so this means that no longer can we approximate the system as linear. So even though the DC bias of the system hasn't changed as well, we see that these new harmonics cause a boost in the DC value. And this is due to that same effect. Using the Fourier series of the input and the transfer function of the system, we can analyze the output further. With simple integration, we can calculate the Fourier series coefficients, and from the transfer function, we see that the output of the system is the sum of the Fourier series times the transfer function at the respective harmonics of the Fourier series coefficients. Since the higher order terms disappear, this summation can be truncated, and while this introduces something called the Gibbs phenomenon, where we see oscillations where we'd expect constant values, the approximation is still good. Obviously, as the number of terms in the summation increases, we'll see that the approximation becomes better. Now, the internals of the audio amplifier also impact the gain on the system. The DC bias voltage determines two important quantities, which is the transconductance and the output resistance. So the transconductance is proportional to the gate to source voltage minus the threshold voltage, and the output resistance is proportional to 1 over the square of the gate to source voltage minus the threshold voltage. So as the DC bias increases, obviously the gate to source voltage is increasing, which means that the transconductance is going to increase while the output resistance is going to decrease. Since the output resistance is decreasing as 1 over square, we'll see that its value is decreasing much faster than the value of the transconductance is increasing. And since the gain of this system is a function of both the transconductance and the output resistance, we'll see that increasing the gate to source voltage is going to cause the gain to decrease. But the audio amplifier system also has a second transistor, and this transistor is needed in order to reduce the output resistance of the amplifier in order to maximize the amount of the signal that's delivered to the speaker. So without the second transistor, the voltage across the speaker is going to be very small, and that can be seen simply through the circuit shown on the screen, in that the output resistance is much greater than the load resistance, and it is absorbing the majority of the output. Now, with the second transistor attached, a new open loop gain can be calculated as shown, with Rout now RO2 in parallel with 1 over GM2, and because GM2 is a very large number, Rout is a very small number. Simplifying the circuit as before, the schematics look nearly identical. However, in this instance, Rout is much smaller than the load resistance, which means that the majority of the output of the amplifier is dropped across the speaker and not the output resistance. There is a downside to this in that introducing this source follower reduces the gain of the system, but this can be compensated by increasing the gain of the first stage. The last component in the system is the speaker, and this is the load resistance, which is, as mentioned before, very small, and this is why the amplifier system is designed to work with a very small load resistance. So there are three main components to the speaker, and that's going to be a coil of wire, a magnet, and a cone. So because the input to the system is varying with a frequency, we see that the field in the coil is going to be alternating with that frequency. And with the magnet inside the speaker, we see that the cone helps to generate these sound waves at the frequency of the input signal. And as long as this frequency is within human hearing range, we interpret it as sound. So with respect to the coil itself, obviously increasing the current or increasing the number of turns is going to boost the intensity. And the other important factor is the material of both the coil and the magnet. And so the permanent magnet obviously will need to be something like neodymium, a hard magnetic material, and the coil should be a soft magnetic material in order to minimize hysteresis losses. So clearly then, the speaker is a type of magnetic circuit, and to solve these magnetic circuits, you employ two different concepts which are analogous to the two Kirchhoff voltage and current laws. So we have the Ampere's law, which is a node law like Kirchhoff current law, and we also have an analogous Kirchhoff voltage law, which allows us to analyze the H time L's through each loop in the circuit. So the key to solving these magnetic circuits is by using the load line of the system, and this is analogous to looking at nonlinear electrical components like transistors, and the equations are very similar as shown. So due to the similarities in magnetic circuits and electric circuits, they obviously can be solved in similar ways. So in summary, the audio amplifier system involves magnetic circuits, transistor amplifiers, and analysis of transfer functions in system. Thanks.